prior to joining the Pritzker School of Molecular Engineering, Professor Amanchukwu was a postdoc at Stanford University and a chemical engineering PhD student at MIT. Let's give him a warm welcome.
Okay, so Felix, thanks for the introduction. My name is Chibueze Amanchukwu. I'm an assistant professor of molecular engineering here at UC Chicago. I was born and raised in Nigeria, and in Nigeria, storytelling through the use of folk tales is a culturally important way to transmit messages across audiences. So today, I will be giving this TED Talk in the form of a folk tale. Okay, so we'll try something new. And when folk tales begin, you say, so the narrator says story time, and then you say story time, and I do it again, and then you do it again, and then we start the story. So are we ready? Story time. Story time. Story time. So once upon a time, let's see if this works. I need to go next. Okay, I'm good now. So once upon a time, Mother Nature saw that man needed to grow, that man needed to prosper, that man needed energy. So Mother Nature said, man, I'll let you use my resources. And so man said, okay. So man looked for living things that man would use to generate energy. So man looked at the trees and cut them down for wood, to burn, to cook, to heat. And then after that, so man kept on cutting and cutting and cutting. And Mother Nature was concerned. You're destroying all my habitats. But Mother Nature knew that eventually man will have to stop cutting because there'll be no more trees left. But man moved on from cutting trees. Man went to animals, used horses to move from X to Y. So man hunted, used oxen to move and plow the fields. But man also hunted for whale to get whale oil so they can power to use for lighting. And man hunted and hunted and hunted. And Mother Nature saw that man was destroying the beings that it had created. And Mother Nature complained. So man said, okay, I'll move to non-living things. So man found coal, the rock that could burn. So Mother Nature was a little bit concerned because it had buried those things for millions and millions of years deep into the ground. But man wanted to bring them up because man wanted to burn coal, to heat water and generate steam, to power the engines that would make man prosper. Because man always wanted to prosper. Okay? So after burning coal and as he burned coal, man found oil that seeped from the ground. And man liked it. So man even dug further and further into the ground to bring this oil back up. And man burned it. Man learned how to refine it to form gasoline. Man learned how to refine it to form chemicals. But what man knew how to do, man knew how to dig and to burn and to burn. And man forgot all about Mother Nature. He didn't need Mother Nature anymore. He didn't need things that lived to sustain the energy that it needed for life. Okay? So Mother Nature, seeing this, vented her fury. So Mother Nature, in an attempt to punish man for the deeds that man had done, Mother Nature said it was going to destroy the very things that she herself had created. So Mother Nature looked at her beautiful glaciers and decided to melt them. Mother Nature, for people who lived close to coast, whenever Mother Nature would have sent simple tropical storms, Mother Nature sent fierce hurricanes. In places that were hot, Mother Nature sent heat waves. In places that were cool, Mother Nature sent cold snaps. In places that had struggles with famine, Mother Nature sent droughts. In places that had excess water, Mother Nature sent even more to flood them. And even forests that showed her beauty, let me go back. Even forests that showed her beauty, Mother Nature burned them all. And man, in an act of penance, cries out, Mother Nature, help! We need to prosper. You can't keep punishing us so. So Mother Nature said, take a look around you. The plants and the animals, do they need to burn coal? Do they need to burn oil to survive? I take care of them using the sun. I give them the energy that they need. So mankind took hint from this. So mankind decided to start extracting energy from the sun. So mankind looked at sand, extracted the silicon, made silicon solar panels. But then mankind even noticed that they could actually extract energy from the wind. And so mankind generated wind turbines and converted wind energy to be able to power and continue to prosper. But mankind knew there was something fishy. It was like, Mother Nature, I think you are tricking us. The sun that you gave us doesn't always shine. The wind that you let us use doesn't always blow. It's like, this is a trick. Mother Nature, like an exasperated parent, looked at his child and said, again, look at the plants and the animals. Because mankind had been used to consuming electricity almost the same instant it was generated. But Mother Nature looked at man and told man, look at the plants. Do they need to always have the sunlight to survive every single instant that the sun hits them? No. If you go to a place like Alaska where you might have 4 hours of sunlight in the day, how do my species survive? How do you as a man survive? Do you always, for every activity that consumes energy, are you always eating? So mankind took a step back and said, oh, energy storage. To store or not to store? That is the question. And so man decided to store this excess energy from the sun, just the same way that plants and animals do that in the world. And so man learned how to take carbon dioxide from the air, take oxygen, take sunlight, to make the fuels and chemicals that it had used oil and gas to do in the past. And so mankind did this, came up with new technologies to be able to convert carbon dioxide, came up with new technologies to convert oxygen to fuels and chemicals. But mankind even got creative. Mankind decided, well, can I even store and make electrical energy storage? So mankind came up with, found a metal A, put it down. Mankind found metal B, put it down. And mankind realized that they had to be dissimilar. And in the middle, mankind put salt water. And man called it a battery. And so within this battery, mankind discovered that they could store electrical energy. But mankind, again, never fully satisfied, goes back to Mother Nature and says, well, with this device I have created, this battery I have created, it doesn't store as much energy as I would like it to store. And so Mother Nature said, take a look at Mount Lithium. And so man looked at Mount Lithium and realized that he could change the anode. Let me go back. So man can realize that he could change the anode from a simple lead to graphite. So you can take graphite from the ground and you can call it an anode. So an anode allows it to, during discharge, releases electrons. And so mankind even got more creative. Mankind developed a new material that did not even exist in nature. Mankind called it lithium cobalt oxide as the cathode. And in the middle, mankind moved away from salt water and replaced it with an organic solvent called the electrolyte. So now man had formed the lithium-ion battery with the graphite as the negative electrode, with lithium cobalt oxide as the cathode, or the positive electrode, with an organic solvent as the electrolyte, and was able to discharge and charge and had the lithium-ion battery. But Mother Nature was still venting her fury. Glaciers were still melting. Hurricanes were still increasing in severity. So mankind needed to act fast. So mankind noticed, well, if I replace the graphite, so that's the anode in the lithium-ion battery, if I replace that with lithium metal, I can significantly increase the energy density of the battery while keeping the cathode the same. But there was still one missing component, one missing piece that remained. What electrolyte should mankind choose? And so, just like again, like a child goes to a parent for so many times, so it runs back to Mother Nature and says, there's still one more piece. I know I have lithium metal. I already have the cathode I created before. What will be the electrolyte I will choose? So this time, Mother Nature said, I'll send you a man. I won't send you the idea, but I'll send you a man. And Mother Nature sent mankind Professor Chibueze Amanchukwu. And so Professor Chibueze Amanchukwu made it his mission to work on electrolytes for lithium metal batteries. And so he invented liquid-based electrolytes. So in these liquid electrolytes, he decided to add fluorine components into the electrolyte to increase their stability, to make sure that they lasted longer. He also incorporated ether-based components that can allow you to have high ionic conductivity. But even that did not solve the problem that mankind had. So even Professor Amanchukwu moved on and also worked on solid-state-based electrolytes. So here is working on polymer-based electrolytes to increase their ionic conductivity and also to increase their electrochemical stability, and then make sure that they're actually non-flammable so that these batteries, when created, do not burst into flames. And so he toiled and toiled and toiled, built a research team at the University of Chicago to solve these problems. But still, time was still not in his favor. So silently, he ran back to Mother Nature and asked, like, how do I speed up this process? How can I discover new molecules faster and faster so we can solve the issues with climate change? And so Mother Nature said, son, again, look at how do I evolve? How do I evolve new species? Through variation and natural selection. And so Professor Amanchukwu thought deeper and said, well, can I use artificial intelligence and machine learning using evolutionary algorithms to help me narrow down the chemical space and discover novel molecules that can act as electrolytes for lithium metal batteries? And so he did, and developed new algorithms and tested them for lithium metal batteries. And Mother Nature kept on watching and watching and watching to see if mankind would discover their solutions as soon as possible to solve the problems that we're facing Mother Earth. To store or not to store, that is the question. Thank you.
Thank you. Thank you very much. All right. Our next speaker is Professor Aaron Esser-Kahn. Professor Aaron Esser-Kahn and his lab's research interests lie at the intersection of biology, chemistry, and material science, and they use the tools from each discipline for the task at hand. Prior to joining the PME in 2017, Professor Esser-Kahn was an assistant professor of chemistry at UC Irvine, and prior to that, he was a Beckman Institute postdoc at UIUC. He conducted his graduate research with Professor Matthew Francis at UC Berkeley. Please join me in welcoming Professor Esser-Kahn.
All right. Thank you for the chance to speak. Let me tell you a little bit about the work we've been doing in my lab, which we call self-adapting materials, or we informally call, have you tried hitting it until it works better? So this is really a question about how do we make things, and why do we make them the way that we do? So basically, we really make things essentially one way. All manufacturing is basically the same, from bottles to cars to computer chips to candy. We make them on an assembly line. We make everything with one process through one system, and we make them all identical. It's because we want to make them fast, right? And what this leads to is we make everything with one purpose and one form, and then it goes out into the world, and it has a discrete lifetime, and it does what it does, and then we throw it away. And the question is that maybe the best way to make things, or are there other ways to make things? Of course, there's been a revolution in the last few years in 3D printing and new ways of making things. We can make customized things these days, but this is very slow, and it still has limitations in the ways that we assemble things and design them. This is in direct contrast to the way that nature makes stuff. Nature does not use an assembly line. It grows everything customized. So how does biology make things? And what advantages do they offer? This is the question we asked and what we started to look at. Biology, if you've looked at it, uses something called genetic adaptation. But even beyond that, everyone's probably familiar with Darwin and his finches and the idea of passing down genetic characteristics from one lineage to another. Beaks can get stronger, they can get smaller, they can get longer. All of that is really advantageous, right? And that's how we get this diversity and plurality of different types of species and finches with different aspects. But what's amazing about biology is not only between generations does it make different materials, But even within a single generation, right? So I have a personal example here. These are my children, and you can see from age sort of 0 to 5, this is how much adaptation has occurred, right? And what you can do is even zoom in further into all of us and look at what's happening. These are pictures on the internet that are replete with these. You know, hopefully everyone's done something like this and not the reverse. You know, what you're trying to do is look at people who have improved their ability to build muscle, right? And what I'm going to talk about is mostly bone, but both of these are true. You can radically alter your physical structure by applying load. And that's just something we don't do with materials currently. And there's actually some really interesting data on this in horses. So you can look at a horse that's been trained, and a trained horse can absorb almost twice as much oxygen as an untrained horse. And this is how we improve horses and make them better at running. And we just aren't able to do that with materials, right? So how can we make materials better with time? What is the mechanism that biology uses to do that? And we looked at bone as the best studied and best characterized material that does this as a model and a motivation for trying to build materials that get better with time and adapt over time. And so bone as sort of a characteristic understanding, and particularly trabecular bone, the bone that's right here at the head of your femur, when it's loaded with stress, it adapts. And actually, you can look at a micro CT of the bone and see that when there's no loading versus cyclic loading, you'll see this improvement in the trabecular area. So the individual lattices will calcify. And so what's remarkable is that every individual's bone is different. And so nature starts with one blueprint, one bone, and then it adapts and modifies across thousands, millions, in our case, billions of different bones that are all customized to exactly the use case that they need to be built for. In contrast, when we build something, it breaks, right? And so we stress test it. And in this case, I'm going to show you different vibrations, and this is going to come back later. Engines, turbines, and compressors vibrate at different levels. Appliances and machinery. Our body itself vibrates, and this is important for how bone adapts. This is a car part being shaken, and of course, you're hearing me speak, and that's actually vibration in and of itself, so audible sound is vibration as well. And these vibrations are what cause the damage to most of our materials, most of the used materials on a day-to-day basis. So the real difference between manufacturing and nature, you could boil down to this idea of a suit that's well fit, a bespoke suit, so something that fits perfectly. That's what nature makes. Everything fits us exactly the way it's supposed to versus sort of an off-the-rack suit. I'm wearing off-the-rack, if you hadn't noticed. But bespoke actually literally means arranged beforehand. So that's what nature is doing. It's arranging and setting up the system beforehand to adapt itself over time, to customize its system in order to be used for the use case that it needs to. And that's what we thought was so interesting. So the question is, as we try and interface materials with the human body, we're going to need materials that work like the human body, because every single person is different. There is no such thing as a standard human being. And if we're going to try and build materials that interface with people, or materials that behave over longer and longer lifetimes, we're going to need to learn these tricks that nature uses. And so one example, of course, is hip replacements, where literally the material is interfaced with that trabecular bone. These have to be replaced every 10 years because the bone can't adapt to the material itself. And of course, if we're trying to put things on the skin, like my colleague Chong is trying to do, this is another place where every single person's skin can vary over 3 orders of magnitude in its modulus. And so we need to think about how to do that better. So the question we asked ourselves is, how do we make materials that make themselves better? And that could be any number of different ranges. You know, stronger, stiffer, more compliant, but chemically adaptable was the goal we were shooting for. So we looked at bone and tried to figure out what are the tricks that bone is using to do that. And if you actually zoom into bone, there's some really interesting studies that have been done here. These are actually pig bones. That's when most of these experiments have been done. It's a little hard to do this on humans. But these are individual points where they've been measuring the modulus of the bone as it's being loaded. There's a lot of data in this slide. I don't really want you to worry about all of that. But just look at this. The point is that as you load this bone, it basically maps the stress field, so the force that's being applied to it, and then replicates that stress field as it's adapting. That's really the key. Bone can understand the stress that it's under and map that stress and then recapitulate it when it's experiencing it. So that's what we started with, trying to understand how we could achieve that and what tricks bone was using. And so there's been a bunch of different hypotheses about how bone does this. And we sort of picked up one that was very old. Turns out it's incorrect. It's not actually how bone does this, but it turned out to be a really great chemical mechanism for how we could do it. And that's using piezoelectricity. And so that's taking sound or vibration. If you squeeze something that's piezoelectric, it generates electricity. It generates a voltage. That voltage can be turned into basically a functional electron. That electron can be turned into a chemical. In this case, it reduces copper from copper 2 to copper 1. That was our earliest example. That copper 1 can then be coupled to a chemical reaction in the form of a polymerization. That polymerization can be used to grow a polymer, which can be used to grow a material inside of a flask. And that growth can be then used to strengthen the material or change its physical properties. So we go from vibration, sound, or the thing that damages the material, to growth of the material, taking the energy that normally harms the material and growing or changing it in controlled ways. This was all done in solution. And as my old advisor used to like to say, you have to get out of the flask in order to do chemistry and materials. And so we moved from that to more and more challenging things. And this isn't actually that odd. If you've ever used a flintless lighter, you've done a piezoelectric chemical reaction before. So if you've ever tried to turn something on, that's a piezoelectric crystal in there. So mechanical shocks often convert things to chemical reactions. It's just that it hasn't been done for polymerization before. That was our innovation. And so we wanted to get to this idea of increasing density or strengthening the material. So we set up a system now where we took these particles, the piezoelectric nanoparticles, put them on the exact same vibrational system that's used to test those car shaking parts. So this exact same system that shakes those car parts and damages them. We put on a polymer matrix. The piezo particles are in there. I'm going to show you the chemistry in a minute, but for right now, just imagine that what happens is that these particles generate the growth of this secondary polymer. That stiffens and strengthens the material. And so as it vibrates, the material gets stronger. And it gets stronger in proportion to the amount it's been vibrated. And so it actually learns and adapts from the amount of vibration it's experiencing. And so this is the chemistry. We use thiolene chemistry here. I'm not going to belabor this. It's a TED Talk. But if you wanted to know, this is what it does. It's step growth polymerization for those of you who are connoisseurs of such things. And these might play or not. But if they do, you can see that when we vibrate it, the material becomes stiffer. When we don't, it remains a very soft and compliant material. And so this is the difference, that we start with this very soft and squishy material. When we shake it, it gets stronger over time. So literally, we're hitting it with thousands of tiny little micro vibrations, and it's getting stronger and stronger as we do that. And we can measure that using rheometry. And this is the overall increase in stress. And in fact, it gets 66 times stronger. It started out very, very weak. So that's a large improvement. But we started from a very low number. And that's what we demonstrated in this paper, that we could make this material that was able to strengthen itself by harnessing the energy around it from its environment. And the last thing that we were really surprised with, that I'll leave you with, we didn't expect this to occur, but we were really pleasantly surprised by, is that when we cut these larger samples open and examined them, there were hard and soft materials inside of the larger sample. And it turned out, when we modeled the stress fields, so the actual stress field that the material is feeling, the von Mises stresses as they're called, it turned out that the material was actually mapping the stress that it was experiencing. So when we did it inside of a flask, it experienced a different stress field. When we left it outside the flask, it experienced a different stress field. We got a little clever. We started punching holes inside of it so that then when there were little points in the triangle, we would get very large stress fields that would concentrate at the edges of the material as we were vibrating it. And we could see then that when we put little indentations in here and sampled the different points, and you could even see here where the polymer is actually spontaneously forming at the edges of the stress fields, the material would respond by basically mapping the stress field that it was experiencing, exactly like the bone was doing. So this was a surprise to us. We had no expectation that it was going to sort of learn and adapt at this level. We just thought it was going to get a little bit stronger, but it turned out it was much more sophisticated than we expected. And so we built kind of the first material that was able to mechanically adapt and learn from the stress fields that it was experiencing using these principles that we applied from bone. So that's the talk. That's the idea. What we think this is good for is applying those principles to all sorts of materials so that we can use them to build materials that go out into the world and learn about their environment and fit people better, fit buildings better, fit airplanes better. They can be used everywhere if you can apply these basic principles of understanding the vibrational structure of the material and applying it in different places. And of course, I want to acknowledge all of the group members who've worked very hard on this, particularly Zhao Wang, who's now an independent researcher. And of course, I want to thank you all for your time and attention. Thank you very much.
Thank you, Aaron. All right, our next speaker is Chong Liu. So prior to joining the PME in 2018, Professor Chong Liu was a postdoc at Stanford University. She received her PhD in material science and engineering at Stanford in 2015 and her BS in chemistry from Fudan University. Her research focuses on design and synthesis of materials, as well as development of electrochemical and optical tools to address the challenges in the water-energy nexus. Areas include resource extraction from water systems, separation in liquid and gas phases, and catalysis. Let's give Professor Liu a warm welcome.
Good morning. So let's start the talk by thinking about what does the future look like. So this is the picture I put up together with the help of my son, a 2-year-old, who doesn't know anything about what the future will look like probably, but he insists that I put a purple house in there because purple is his favorite color. We know that in the sustainable future, we need the renewable energies to power everything. And we need the solar power, we need the solar panels, we need the wind turbines. And for transportation, we need electric vehicles. For communication, of course, we cannot live without our laptops or mobile phones. Probably we'll just have more and more personal electronic devices. And if you look at where we are now to where we are going to be, actually there is a big gap. So currently, the market penetration of electric vehicles, solar, and wind is only 3% or 4%. So what we want to be is, for the sustainable future, 30 to 40 or even 50%. So the target is easy to say, but as an engineer, you couldn't help wonder, how are we going to make all these devices and with what? So inside all these renewable technology devices, there are actually very complicated components. They are made of tens and hundreds of different components from different chemicals. And we are just going to take a closer look by breaking down into their most basic building unit, the element. Sorry, mine is not forwarding. Yeah. Okay. So if we want to make solar panels, you need a lot of silicon. And for the wiring and packaging, you need aluminum, copper, and a lot of plastics and organic. And for the, is it work? Oh, is it me or? Sorry. So for the wind turbine, it's even more complicated. You need a lot more elements. You need the rare earth element, you need steels, which is iron and carbon, and you need the packaging, the wiring, which is aluminum, copper, and you need a lot of silicon. And for the transportation, sorry. Okay. Yeah. So it's just a simple click. Okay, so for the car batteries, we need the mobile ions, the lithium ions, and we need transition metals, the cobalt, nickel, manganese. As well, we need the current collectors, the copper and the aluminum. And all these are the elements we need. Do we have them? So this is the periodic table. This is the bank of wealth we have. And we can use them to make every material, almost anything. But we cannot choose freely from this periodic table because, as you can see, a lot of these elements are highlighted with orange and red colors. So 44 out of these 118 elements are endangered. That means that they will be facing a severe supply security issue. And if you recall what we just talked about, and among these elements we have lithium, transition metals, and the rare earth element, and also the ones that make your transparent electrode for your cell phones. And if we cannot use them freely, so what's the problem? Is a supply security issue equivalent to an element abundant issue? So actually, no, at least not for all of them. So these metals are rare. They are noble metals. They do exist in a rare amount on Earth. But a lot of those elements we see, they are not rare. Even the element called rare earth, they are abundant. So what's the problem with mining? Why can't we get all these materials? So the first thing is, the elements are not distributed uniformly. So this is an example of lithium. A few of the countries are very lucky that they have easily accessible resources that are very concentrated, that you can mine with a simple method, and you can mine with profits. Such as here, 10 countries account for a lot of the resources for lithium, and all the rest of the world only counts for a little bit. And another problem with mining is that this is what we typically do for ore mining. And if we are going to sustain or supply all these elements, if we're keeping doing this, then we will make a huge cost to the environment. And we will make a lot of pollution to the land and to the water. As well, we have to deal with a lot of the acid, tons and tons of acid waste it generated. Do we have other options? So if you take a different angle to look at the Earth, actually the Earth is covered 70% by water. We have oceans, we have lakes, we have rivers, we have salty lakes, brines, geothermal brines. We have many, many different kinds of natural water bodies. And we all know that in those waters, they have salt. They have minerals dissolved. Can we use those salts? The challenge is that the salt is very, very dilute. Even though the lithium-uranium amount in the ocean is hundreds and thousands of times more than that on land, but they are very dilute. Okay, challenge accepted. So this is what we do. So in our group, we do separation and mining. We want to develop a new method and new materials to promote the separation efficiency. So here is a platform we developed. We want to harvest the electrons from the renewable resources, the solar and wind. And we use those electrons to power electronic devices or electrochemical devices. And in these electrochemical devices, you have two electrodes. And the negative electrode here is the one that's doing the work. So you are pumping electrons to these negative electrodes, and the electrons will induce a redox reaction. And to balance the charge, you will be injecting all the ions from the aqueous environment to concentrate them into your solid electrode materials. So this part is the core of what we develop, what we work on, we design. So now let's take a closer look to the atomic and molecular level. So when you are going to inject electrons into your materials, all the cations, the positively charged ions, will be concentrated on the surface of your electrode. They all want to get into the structure. And how can you do to selectively only put lithium into here? So we designed the material to have a very confined channel that it only allows unhydrated ions without any water with it to go into the channels. Lithium has the advantage because it has only monovalent charge, the less charge than the other type of ions, and it's very small in its ionic diameter. So in that sense, when lithium travels through a solid, it's much faster than the other type of the ions. So that's a huge advantage to achieve a lithium selectivity. And this is the core part of our innovation. But at some very dilute concentration, sodium will start to compete again with the lithium because they just look very similar. They are like cousins. and they want to sit into the same structure. And how can we deal with that? So we turn to advanced characterization tools. So we want to have a deep understanding of how this lithium and sodium are competing in the same wholesome inorganic materials. So if you look at all these pictures, we have the atomic resolution views of the atoms. And the lithium and sodium, they don't like each other a lot because they still have a big diameter difference. So what they tend to do is that they tend to separate apart in these materials. So this is a knowledge we gained by studying two types of different materials. And guided by this principle, we can design different kinetics pathways or different phase equilibrium to guide the lithium to go into the structure, but prevent the sodium to go into the structure to keep promoting the lithium selectivity in this case. Still, what we can do now is what we can achieve now is very, very exciting. We can concentrate the lithium from the ocean with a ratio of lithium to sodium 1 to 20,000 by one pass to almost 1 to 1. So, but we are not satisfied by this result. We want to get a much higher selectivity to all lithium recovered. Is that possible? So this will be something we keep working on, and we will keep working on to make sure this material runs for hundreds and thousands of cycles, that it can last for tens of years in use for mining. And most importantly, we want to develop this electrochemical platform for many critical elements as possible to really enable a green and sustainable mining. Thank you.